This is the second part of the causal design lecture. What I'm going to do in this part is walk you through some common pre-experimental designs, and then we're going to talk about the threats to internal validity. So remember what internal validity is. Internal validity means that when you see some effect, you can unambiguously attribute that effect to the independent variable, the causal factor. And you can rule out other spurious causes. So let's start out with what's the simplest pre-experimental design, the after-only design, also called the one-shot case study. So in this design, you do something and then you take a measurement. So I like to map this back to the statistics that we've studied. The way to think of this design is we're in the first part of chapter 10 with the single sample t-test. So any of the problems that we did back then would be one of these problems. So recall that we had the delivery system problem where we were considering a new delivery system. So we chose 48 packages at random. We sent them out with the new delivery system, and we saw how long they took to get there. So the new system took a certain amount of time. We then compared that with some constant, some fixed constant, which was the amount of time that the old system took to get there. So that's an after-only design. Another example is I'll call the recall study. So recall is it's an old measure of advertising effectiveness. So let's say that we put an ad on a television show last night, and then today we call up 200 respondents, and we call up a bunch of people to get 200 people who said that they watched that television show last night. We then probe whether or not they saw our ad. So I'll ask, let's say our ad is for a Toyota Camry. So then I'd ask about the category of interest. So do you remember any automotive commercials that appeared during that show last night? And if the respondent said, oh, there was that really cool Toyota Camry ad, then that's classified as unaided recall. If the respondent can't remember any ads, then the interviewer prompts the person further. So do you remember seeing any Toyota Camry ads? And if they say, oh yeah, okay, I remember that one. They had some curves and they were going around really fast. That would be called aided recall. So the percentage of people who have unaided recall is called the unaided recall measure. The percent who can do aided recall then are another measure. Okay, so this is an example of a one-shot only case study because you do something, you show the ad, and then you take a measurement. There are a variety of companies that provide norms. So you should have a recall score of such and such if it's a good ad. So you're comparing the mean against some constant, this Burke norm. In the same way that with the delivery problem, we were comparing the new delivery times with the established constant that we know from the old system. Right, this is a pretty poor design. Provides absolutely no basis for comparing what happened in the presence of X versus when X was absent. So it's very easy to shoot holes in one of these designs. So let's go back to the delivery system problem. The delivery system has all sorts of threats to internal validity. So the most obvious one would be weather. So let's say that baked into our established delivery time for the existing system is all types of weather throughout the year. So in that, We have snowstorms, we have thunderstorms, we have bright and sunny days without any weather disruptions. We have all of the above. Now, let's say that in that delivery system we found the new system was better, but let's say that the day we happened to send out our 48 packages was a bright and sunny day without any thunderstorms, without any snowstorms. Then it's not really a fair comparison because the old system has baked into its number all those snowstorms. So a much better comparison would be to do a randomized controlled experiment where you have two groups. We pick 48 packages, send it with the new package, and then compare that against packages sent with the old system on the same day. So you want to hold all those conditions constant. All right, and that would have much more internal validity. If you want external validity as well, maybe you want to test both systems both on a day when there's thunderstorms as well as bright and sunny days, and then you'd have really strong external validity as well. Let's take a look at another pre-experimental design. What we're really doing here is moving through chapter 10. This is a design we've already discussed. It's the before-after design, where you take a measure, you do something, and you take another measure. Now, sometimes this design is okay, but often it's not. So this is the paired sample t-test, by the way. Now, let me give you two examples. One's I'm going to call the copy testing example. So with copy testing, what happens is you invite subjects to some location. So often it's a hotel ballroom. And you invite them in under the premise that they're going to evaluate some new TV programs. We would love to get your opinion on these new TV programs. Then what happens, once people arrive, you give them a booklet with a questionnaire, and you ask them a variety of questions on a lot of different topics. Sometimes they'll do something like this. There's going to be a drawing for a prize. Since you were here, tell us which of these brands you'd want in your prize basket, since we want to make that prize basket relevant. And so that's a very subtle way of getting at brand preference. Sometimes they'll ask you about attitudes towards brands on that pre-measure booklet. Anyway, they take this pre-measure in one way or another. Then they sit and watch some TV programs, and embedded in those TV programs to make this as realistic as possible are some advertisements. So the advertisements are the treatment that you really care about. After the program, you give them another booklet, and you ask them about their preferences on brands, their attitudes, all those sorts of things. Those make up the post measures. What's often done as a subsequent post measure is they call up the people the next day and ask them about recall measures and so forth. So that's an example of a before-after design. The heavy up advertising example is as follows. Let's say that we monitor our sales of some packaged good product for 1 week. Then we do something to our advertising. So we double our advertising budget, perhaps this is on in-store. And then after doubling our in-store advertising budget, we measure our sales. So it seems like a good design, right? Have a pre-measure, and then we measure what happens after we've done that. Turns out this is not a very good design. So what I'd like to do at this point is to walk you through a variety of extraneous factors. So these extraneous factors have been categorized to kind of help us keep track of them. And I think these categories are kind of helpful. So it's good to have these names for the threats. When you're in a meeting, you don't necessarily want to use these names. You want to point out specific threats or identify specific threats. But having these categories will help you, think of the specific threats. So the first one is called history. So History refers to other variables or events other than the one manipulated by the experimenter that occur between the pre and post measures. These other variables also affect the dependent variable. So it's very easy to come up with examples of history for the heavy up advertising example. So any external event. So what happens if your competitor at the same time increases their advertising or cuts price? Okay, let's go draw a picture of what could happen. I'm gonna go over to the sketchbook, and here's the diagram: O1x, O2. Let's say our sales in week 1 are 10, and let's say the effect of of doubling the ads is 5. However, our competitor at the same time decides to cut price. Here's the competitor cuts price. And if the competitor cuts price, let's say that hurts our sales by a -3. So what do we observe in period 2? Well, we observe 10 plus 5 minus 3 equals 12. Now, the effect of the treatment here is O2 minus O1. So we would conclude that the effect of the treatment would be 12 minus 10, which is 2. And we'd come to the wrong conclusion about the effect of our change in advertising. So that's a big problem. So here we have a threat to internal validity. We observed an effect, however, that effect is not correct because it doesn't account for this. Now, let's jump ahead to a true experimental design. A better way to do this would be to have a treatment group and a control group, and you take pre-measures on both. You double the advertising in certain stores, you leave the advertising constant in the other stores, and then you take a post measure. Now, let's say that our pre-measures are 10, so we make sure that we have matched stores. Let's say the effect of the treatment is a +5, and let's say our competitor still cuts price. Well, what happens here? We're going to observe a 12 here. What are we going to observe here? Well, we're going to observe a 7. Now, the effect of the treatment in this case is going to be O3 minus O1, so that's the effect on the treatment group, minus O4 minus O2. That's the effect on the control group. So let's see what happens. 12 minus 10 minus, okay, what do we have here? 10 minus 7, which is equal to 2 minus a -3, which is equal to 5. So notice a controlled experiment, which has this basis of comparison, gets to the right answer. So it correctly sorts out what's due to the competitor and what's due to the treatment. That's why it's really important to have one of these control groups. So there's any number of these examples. The economy could decline. There could be the financial crisis that hits. A war could break out. So all of these would be examples of external events. Maturation is another class of things that can go wrong. So maturation represents a biological or physiological change that occurs at the same time between the pre and the post measure. So let me give you some examples of maturation. With the copy testing example, I come in after work, I'm well fed, my adrenaline is running, is pumping because I've just rushed, to get from my workplace, picked up some food along the way and got here. Then you give me a questionnaire. Next, I watch a couple hours of TV, and my God, I've been up since 5 o'clock this morning. I'm tired. I'm now hungry again. I'm kind of grumpy because it's getting close to my bedtime, and now I have to take another survey. So the subject, the subject, am in a very different state of mind when I take the post-survey than when I took the pre-measure, the pre-survey. And so I might respond very differently because I'm tired, hungry, and grumpy, as opposed to because my attitudes have been changed due to your advertising. With the heavy up advertising, there could be biological changes to the store where we rearrange things. The aisles have been rearranged, or the place there's a different end cap that's siphoning off the sales of my product. Experimental mortality is kind of hard to come up with good examples in marketing, but there are really good examples of this in medical studies. So I'm not going to dwell on this. This isn't a medical research class, but it's probably worth giving you an example. So different experimental mortalities where you have differential loss of respondents between the two groups. Let's say that I have an experiment where I'm testing some medicine. And this medicine happens to have some nasty side effects. So let's say I have a randomized controlled experiment where some people get the real medicine, some people get a placebo medicine, which is just a sugar tablet, but it's disguised as the medicine. And what's going to happen? So the treatment group gets this medicine and it has all these nasty side effects, and the people in the treatment group are not very happy being part of this medical study because the medicine is making them sick. So they drop out. Those who don't like the side effects drop out. Those who are real hardy and strong stay in. Whereas in the control group, you don't have any differential loss because the sugar pills have no effect on people. It's inert substance. So you may come to very different conclusions because of that selection bias, that only the hardiest people stay around in the treatment group. So that would be a threat to internal validity. There's two sets of testing effects. There's the pre-measure and the interactive testing effect. So let me go over these with you. I'm going to clear the page here. Let's say that I take a pre-measure, I do something, and then I take a post-measure. The pre-measurement effect is where the act of taking a pre-measure affects the post-measure. The interactive testing effect is where the act of taking a pre-measure affects the way the respondent responds to the treatment. I'll give you some examples of this. So a few years ago, I was involved in testing a speed reading product. So the speed reading product involved sitting through a couple hours of training, and you learned how to do speed reading. And so I was asked to evaluate this product and test a couple things. So did your comprehension change? So they wanted to be able to claim that your comprehension did not change. And did your reading speed change? So we ended up doing a design like this. Now we gave the participants a passage from a magazine. So there was a magazine article. We asked them to read it. We recorded their time and then gave them a little quiz to measure comprehension. So we took a pre-measure. Then these subjects sat through a couple hours of training, and then we had them do another reading and had them take another test on comprehension. Now, what would happen if we use the same reading in both periods? Well, obviously, it's going to be easier to read that article and understand it the second time around. So if I've read something and then 4 hours again I read it again, it's probably much easier the second time around. And 4 hours isn't that long. I probably remember a lot from the first time. So the act of taking a pre-measure would affect the post-measure. There are other instances of this So sometimes when people take a standardized test for the first time, they they don't do very well. Then they go to some test preparation class, and then they take it again. Well, the fact that they've already taken the test once means that they kind of know better how to take the test. So if there's a change, is it due to that test preparation course that they took, or is it due to the fact that now they're taking it the second time and they kind of know how to use their time better? Are they better just at taking tests? So these are examples of pre-measurement effects. So let's talk a little bit about the interactive testing effect. So suppose in this pre-measure I ask you certain questions about the Toyota Camry, if this is a Toyota Camry ad. And maybe the communication objective of the ad is to talk about the gas mileage of Toyota Camry. And so I want to find out whether that communication objective has been achieved. So up here, I take a pre-measure of your knowledge of the gas mileage of Toyota Camry. So I ask you, what do you think Toyota Camry's gas mileage is? And you don't know. You really have no clue, so you just check off a box. Then 15 minutes after you take this pre-measure, you're watching television, and on comes a Toyota Camry ad talking about gas mileage. Now, you were just asked a question about gas mileage that you didn't know. You might pay more attention to this ad that's giving you the answer. Had I not asked you those questions, you would have just slept through the ad. All right, so here's an example where the act of taking a pre-measure is going to affect the way you respond to the treatment. You're actually going to pay attention as opposed to falling asleep. So that would be an example of the interactive testing effect. Let's talk about instrument variation. Instrument variation is when you have a change in the measuring instrument occurring between the measurements. So let's go back to my speed reading test. So to avoid the pre-measurement effect, what do? You've got to have different readings and a different quiz then. So you have some people read, well, you have the people read, article A here, and you give them the quiz with that. And here you have them reading article B. The problem with this approach is that you open yourself up to the instrument variation threat. So what happens if article B is much easier, or it happens to be something that my subjects just know more about? For some reason this is easier than this. Then I would observe a change in comprehension. Maybe I observe an increase in speed that's really not due to the treatment. Instead, it's due to the fact that the reading is easier. All right, so that's interactive, sorry, not the interactive, instrument variation. What's the remedy for this? Well, you have two groups. Here you have, you give them reading A, then they do the treatment. Then you give them reading B as the post measure. You have a different group with random assignment. Let's do random assignment. Who first reads article B. They also get the treatment, and then they get article A. And so then, if B is easier than A, you'll be able to sort that out when you compute your differences. So that's how you avoid instrument variation. There's lots of ways for this to occur. Another subtle way for instrument variation to occur is by having a different interviewer. So if we have interviews and one interviewer is very enthusiastic, very gregarious, and the other one's kind of grumpy, that would also affect measurements. So if you have a grumpy interviewer here and a very lively interviewer here, you could observe a change that's not due to what you test, but is just the interviewer. Placebo effects. So placebo effects occur when the knowledge of being treated changes changes behavior. So it changes the way that people respond. So one really good example of this is the two-foil example from Churchill's marketing research book. A two-foil is an example of a product, and this product was supposed to increase your gas mileage. So it was you'd buy a can of two-foil and you're supposed to add it to your tank of gas every time you filled up, and the claim was that it had special lubricants that would make your engine run more efficiently, and therefore you get higher gas mileage. So there was a study done where it was essentially one of these before-afters, and we measured a person's gas mileage. We said, okay, here's some two-foil, put it in your gas tank. And then here is, let's measure your gas mileage after you do that. And so let's say the gas mileage here was 24 miles to the gallon, and it was 28 miles to the gallon here. So the claim was two-foil improves gas mileage. Subsequently, they did randomized controlled experiments and found that two-foil had no effect. So why was this? Well, what happened was that by telling all these people, okay, this two-foil is going to improve your gas mileage, now they're in this study, they changed their driving behavior. So they drove less aggressively, they coasted more, they accelerated more slowly when they came off a red light. And so because they were driving differently, the gas mileage went up. It wasn't due to the two-foil. What I'd now like to do with you is have you discuss how you would design an experiment to avoid this placebo effect. So what would you do differently? And we'll have this as a discussion board question. So that's the placebo effect. Moving on, though, we'll have that discussion offline. Here's another example that you can read about where it was purely a placebo effect. One other term that you should know is double blind. So double blind is where both the subject and the investigator are kept unaware of whether they're in the treatment. So if you have a doctor who has to make a subjective judgment and he knows that you're getting the treatment, that doctor may come to may have an unconscious bias. So therefore, you want to keep the doctor blind as well. A few more designs for you. Static group comparison. This is where you have two groups, and subjects self-select into the two groups. You do, one group gets a treatment, the other one doesn't, and then you take measurements. So here are a couple examples. Two groups of respondents are recruited on the basis of convenience. So for example, one could be shoppers in the morning, the other could be shoppers in the afternoon at this department store. The morning group is shown a TV commercial. Both groups are asked about their attitudes towards the store. Well, the biggest problem with the static group comparison is that you don't know if the groups are equal to begin with. So let me illustrate this. Here's a static group comparison, X, 01, 02. So let's say these people have an attitude of 4 on a 5-point scale. These people have an attitude of 3. So it appears that that ad had an effect of 4 minus 3, which is 1. But what if people in the morning are just systematically different? People who shop in the morning are very different than people who shop in the afternoon. If you ever go into a supermarket in the morning, it's a lot of old and retired people there. In the afternoon, it's people getting off work and so forth. So just very different people. So what would happen if the pre-measure, if we'd had a pre-measure, had been 4 and 3? So the groups are different to begin with. Well, the effect of the treatment here is 4 minus 4 less 3 minus 3 equals 0. Okay, so you'd come to the wrong conclusion because the groups were unequal to begin with. So that's the main threat in this experiment. You have no knowledge of whether the groups are comparable. Another example of this is with magazine experiences. We've already talked about this with the independent sample t-test. But the treatment in my case was being engaged with a magazine. So to what extent are you engaged with the magazine? Then we showed them an ad and measured their attitudes towards the ad. So does your engagement with the editorial content of a magazine rub off on the ad? So if you think a magazine is very prestigious, does that carry over and affect your luxury brands? Well, what you don't know is whether the groups have equal responsiveness to advertising in the first place. So are they different on that variable? Another way around this issue is to control for other possible confounds through multiple regression, and you'll learn all about that next quarter. So what we've just seen is an example of a selection bias. Selection biases occur when the two groups are unequal to begin with. What do you do to avoid a selection bias? There's a couple things that you can do. The absolute best thing is to randomly assign subjects to treatment and control. So if you do that, then you randomize away those differences, and so you would expect the two groups to be equal. Another remedy is to do matching. So instead of randomization, you have some pre-measure that allows you to assign them. So this is often done with stores. For example, you might be testing the effect of in-store displays, and you know that some stores are small and other stores are large. So then the idea would be to take two small stores and then put one of those small stores in the treatment group, one in the control group. Then you take two medium-sized stores and assign them accordingly. Statistical regression is a special type of a selection bias. So statistical regression occurs when you assign people to the two groups based on a pre-measure. So people who are high get assigned to one group. People who are low get assigned to another group. Classic examples of this regression effect is the Rookie of the Year example, closely related to the Sports Illustrated cover phenomenon. So let me run you through these. Every year in baseball, they give the best first-year player the title Rookie of the Year. So if this is your first year in baseball, you're eligible to win this award, and the best of all the first-year players gets this Rookie of the Year award. Now, over an extended period of time, the batting average for Rookies of the Year was 285. If you don't know anything about baseball, batting averages just tell you how well that player did. So higher means they did better. And notice that these rookies were much better than most baseball players who only had an average of 257. But it's well documented that people who got the Rookie of the Year award usually don't do very well or as well in their second year. So among all the Rookies of the Year, in their second year they only bat 272. So their average goes down. And sports writers have known about this for years. They call it the sophomore slump. And their explanation is that they get a big head, they don't work as hard, and they get too distracted by endorsements and such. That's the reason, that's the explanation for the drop. Before I discuss this, let me describe the Sports Illustrated cover phenomenon. So the Sports Illustrated cover phenomenon goes that if you get your picture on the face of, sorry, if you get your picture on the cover of Sports Illustrated, next week you do badly. So it's as if having your face on the making the cover of Sports Illustrated jinxes you, and your performance drops the next week. And again, people claim that having your face on that cover is the cause of your decline. Well, both of these examples are regression effect examples. So what's happening is you're using a pre-measure to assign people to a treatment group. In the case of the Rookie of the Year example, you're going to use the first season to assign certain people to the Rookie of the Year class, and then the rest stay in the other class. And what let me describe what's probably happening to these Rookies of the Year as opposed to being affected by endorsements and so forth. I'm going to draw a little graph. Let's say that this is your performance. So in the case of the Rookie of the Year example, it's the batting average. And let's say that your performance is a function of your ability. Moreover, let's say that there's a positive association between your performance and your ability. So people who have more talent will perform better. People who have less talent will perform not as well. This relationship, however, is not deterministic. So it's not like there's a one-to-one association. There's some randomness. So if you're a really good player, the distribution of your performance will have some element of randomness to it. So sometimes you get lucky, sometimes you don't. I mean, the most obvious example of something like this would be free throws. If you have a free throw shooter and he's a good free throw shooter, he doesn't get the exact same percentage of free throws every night. So some nights he gets the bounce. He shoots the free throw and it hits the rim, bounces up, and then drops through the hoop. Next night he hits the rim and it's 1 millimeter off, it bounces up and then goes out. He doesn't get the basket. All right. So the point here is that within a given level of ability, to some extent your performance is determined by randomness. In baseball, sometimes you guess right. You're the batter. You guess you guess right that it's going to be a curveball, and you hit it out of the park. Other nights you guess wrong and you strike out. So there's a certain amount of randomness. All right. So given that you're a high ability player, we're going to choose one player to get the Rookie of the Year award. Who's going to get it? Well, the person who's going to get it is probably someone who had a good year. So they're up here. Now, if my performance during my rookie season was up here, what do you think is going to happen to me next year? Now, assuming there's no big shift in this curve, if I got much better, I'd shift out, but that's probably not going to happen, such a dramatic shift. Where am I going to go? Well, most of the area is down here. So I had one student describe this once as a high watermark. So the Rookies of the Year get assigned, to this award, but chances are next year they're going to go down. There's not much area up here for them to go up. There is some area, and there's some rookies do better in their second season, but that's pretty unlikely. All right, so that's an illustration of this regression effect. Let me give you a marketing example of this, a couple of marketing examples. One is you never do as well in test as you do in rollout. Sorry, you never do as well in rollout as you do in test. This is a saying from direct marketing. It comes from testing lists. So direct marketers will buy names from a lot of different sources. They don't know whether these sources will work very well, so they test them. They send out 1,000 catalogs or 1,000 offers to the American Airlines frequent flyer database. Send out another 1,000 names to the Heart Association database. Send out another 1,000 names to some other list. Then in those tests, the ones that do well get rolled out. And by rolled out, what I mean is the organization buys more of the names and then sends to more people. Well, what happens is that same thing. Those that test well get rolled out, and then of course what happens when you do a rollout, you send out a whole lot more, and when we all know that when the sample size increases, the variation decreases. So remember, sigma sub p is pi times 1 minus pi over n. So as n increases, that standard deviation gets a whole lot tighter. So if you test up here, and then notice there's no area under the rollout curve for you to go up. So that's why your rollout scores go down. Another example of this might be with loyalty programs. So if you have to fly a certain number of miles to get into the gold tier, those who get into the gold tier may not perform as well the next year. So that's why loyalty programs reevaluate their customers pretty often. They don't have a perfect way of assigning people to get premium treatment versus base treatment. So those are all examples of the regression effect. Here are a couple examples of what can affect external validity. So surrogate situations are where things occur in a lab setting. So if you think about copy testing as really a lab setting, it's very unrealistic. You have forced attention. In real life, when a commercial comes on, people go make themselves a sandwich or switch the channel. Whereas in that hotel ballroom, you have forced attention. You can't leave. You can't go to the bathroom. You can't go make yourself a sandwich. You can't change the channel. Measurement timing is where what you learn in summer may not apply during winter, or what you learn during a holiday may not apply when it's not a holiday. So those are all measurement timing effects.